So when ethyl ethanoate which is also known as ethyl acetate, is treated with sodium ethoxide followed by an acid workup here, ethyl 3-oxobutanoate, also known as ethyl acetoacetate, is formed. And that is called a beta-ketoester. And so if you look here, this is the ester, this is the alpha carbon, and that's the beta carbon, and there's a ketone here on the beta carbon, and that's why it's a beta-ketoester, right? This is an example of a Claisen condensation. This was named after Rainer Claisen, who developed it. He lived from 1851 to 1930. You can see his photo here. It's a condensation reaction because two ester molecules are fused together, and a smaller molecule, which in this case is ethanol, is eliminated. Now, right? So let's look at how this reaction works. So when we look at this mechanism, I am going to draw, so there's our ester, right? And I am going to draw the two hydrogens here, okay? Well, there's three actually. But it's important to note that a successful Claisen condensation requires two hydrogen atoms on the carbon next to the carbonyl carbon of the ester group. Okay, because both of those are going to be removed. You have to have at least two because they're going to be removed. So there are three here, so we're totally fine. And so the first step is a proton transfer. Where these electrons come and they steal a proton, and when they do that, those electrons go back on that carbon. Now, when that happens, we end up with a negative charge on that carbon. Now, this is resonance stabilized, and you can draw the resonance structure. And then the next step is a nucleophilic addition, where we have this second molecule. So it's just another, remember, this is a reaction. There's lots of molecules running around in this flask, and another molecule comes along. And what happens here are these electrons come and they attack that carbonyl carbon. When they attack that carbonyl carbon, those electrons go up onto the oxygen. And now we have this guy. Okay, and so this is going to go through a nucleophile elimination where these electrons are going to come down here and these electrons leave. Okay, when those electrons leave that bond and go onto the oxygen. Okay, when that happens, we have this guy. Now, here's the deal. When we look at this, what you're going to find, right, is this reaction only works if there are two hydrogens. There's a proton transfer here. where right, this is going to come in, it's going to steal that proton, those electrons are going to go there, okay? And then the reaction stops here before the acid workup. And so at the acid workup, you end up with another proton transfer. Right there. And there you are. There's your molecule. This second proton transfer step, well, let me back up. The second proton transfer step here is irreversible, right? And that means it's going to heavily favor the product side. And that step's irreversible because the beta-keto ester is much more acidic than the normal ester because of the resonance delocalization of the negative charge of the enolate anion that's produced. Now, this is really important because the first three steps, this step, and this step, right, are reversible, and they generally favor the overall reactants here. So the deprotonation here on this step, right, is what shifts it to favor products. So that's how we know, because if you look at this, right, you're like, hey, why did we take off a proton here just to put that one back on, right? How do you know it just doesn't end here? Well, the reason is because if we use a molecule that doesn't have the second hydrogen on it, this reaction doesn't work. So because this reaction favors the reactants, and then if a little bit of this does get made, this reaction still favors the reactants, and a little bit of this gets made, this reaction still favors the reactants. It's this that's irreversible, right? And then when you do the acid workup, you get your product. And so that's how we know that this is part of this reaction. So as I tried to kind of poorly explain on the previous slide, right, a successful Claisen generally requires at least 2 alpha protons, right, on the initial ester. And without the first alpha proton, the enolate anion couldn't be produced. And without the second, the equilibrium would favor the overall reactants. And so you would have no significant amount of ester to be isolated. So it's through reactions that we have shown this. So let's do an example. Draw the ester that can be used in a Claisen condensation reaction to synthesize the compound shown here. And so when we do this reaction, the first question we need to ask ourselves is, which carbon-carbon bond in the beta-keto ester would have been formed in a Claisen condensation? Okay. And so when we look at this, it's important to understand, we find the ester and we say, okay, look, well, it'd be helpful if I could draw the alpha really well. There's the alpha and there's the beta, okay? And the new bond is going to be right here between this alpha and beta carbon. And so we need to apply a transform that undoes these two so that then we can put them together, kind of like pieces of a puzzle, right? So when we look at this to undo this transform, and I may just do this kind of up here so that I don't have to draw that again, right? And I think about, okay, if we're going to undo this, I am going to draw and look and say, okay, this guy is going to be one piece, right? And so if that is the case, all here, it's going to be 2 of those that react, right? And so the answer here would be, oops. just like that. There would be 2 of those, okay? So that would be that's the easiest way to figure out the ester that's used to synthesize the molecule, all right, is to locate it like that. Now, I want to point something else out here. In the Claisen condensation reaction, the base that's added is the ethoxide anion. It's the same as the leaving group that departs in step 3. The reason for this is, and so I want to show this to you here, right? Sorry, there's a weird noise in my house. I'm not sure what that was. So the reason is, if the base were an alkoxide other than an ethoxide, then the transesterification would produce an ester that's different from the starting material. So you can see that here. The alkoxide that's shown here is a poor choice because it produces a different ester via the transesterification reaction, right? If hydroxide were used for the base, then saponification, right, would irreversibly convert the ester to a carboxylate anion. These problems are completely avoided when ethoxide is the base. Transesterifications still occur, but the esterification product is identical to the initial ester. So I also want you to notice that the solvent, which was ethanol in the previous reaction, is the conjugate acid of the base that's added. Other choices of solvents can lead to unwanted transesterification or saponification reactions. And so we want to try to keep those as the same so that we don't get any unwanted side products. So what this comes out to look like is for a Claisen condensation reaction, unwanted transesterification and saponification reactions can be avoided if the base that is added is the same as the alkoxide leaving group of the ester, right? And the alcohol solvent is the conjugate acid of that base. And so these R groups all have to be the same. It's the best way to do it, right? So that you don't get any unwanted side products. So when you're designing these syntheses, this is what you want. Now, maybe the question you want to ask yourself is, well, do we have to do the Claisen reaction with 2 of the same molecules? And that what you're trying to ask really is about a Claisen condensation reaction that's called a crossed Claisen. So if you want to do a Claisen condensation reaction involving 2 molecules of the same ester, that's a self-condensation. So 2 molecules of the same ester, that's called a self-condensation. And that's what we've been talking about, really. Okay? Now, a Claisen, like I mentioned, can also involve 2 different esters, right? And that's called a crossed Claisen condensation. Now, these reactions really, you have to really think about them because they can potentially lead to a mixture of condensation products. And so look at the color coding here. If you are doing this crossed Claisen condensation where we've got this ester in red and this ester in black, and they're different esters, you can get up to 4 different products. So you can get self-condensation with this molecule, right? You can get one cross condensation here, one here, and then self-condensation with this molecule. So that's a lot of products that you then have to figure out and separate. Now, if only there were something we could do, right, to try to prevent this, which I'm sure is what you're thinking right now. So one way to avoid producing a mixture of condensation products in a cross-Claisen is to ensure that one of the esters has no alpha hydrogens. Because remember, right, if we don't have any alpha hydrogens, we can't do this reaction. And so here are some common esters that don't have any alpha hydrogens. And so these can be dissolved in solutions with an alkoxide base without initiating a Claisen condensation reaction. And then a second ester that has alpha hydrogens can then be slowly added to this solution. Now that being slowly added is really important because if you add it too fast, right? So let's look at this. So this ester has no hydrogens. So once you put it in here, it's not going to undergo that self-condensation. You want to add this guy really slowly. If you add him too fast, then all of a sudden this will start reacting with itself, okay? So you add it really, really slowly, and we can get a crossed aldol condensation here. Now, look, that's still 45% yield, right? So it's not a super, it's doable, but it's not a super great yield. Other examples of this, when we look at this, right, aldehyde and ketone enolates can also undergo these nucleophilic addition elimination reactions with esters, right? The products here are considered to be 1,3-dicarbonyl compounds. Right? And the reaction in equation 2343 is very synthetically useful because the ester has no alpha hydrogens. And then here in 2344, the ester has alpha hydrogens, but the reaction synthetically useful because the ester is significantly less acidic than the ketones. So these are two reactions that work really well as a cross-Claisen condensation. Let's do an example. Okay, so how would you synthesize this compound in a Claisen condensation reaction? So when we look at this, right, and think about it, we say, okay, which carbon-carbon bond would have been formed in a Claisen condensation? And so again, we need to look at the alpha and then the beta carbons, okay? And so when we do this, we want to see if we can do this in such a way where we can get no alpha hydrogens, right? And so if we divide the molecule here, okay, then our precursor would be there, and then with no alpha hydrogens, and then butane 2-one or 2-butanone here. So this would end up helping us. So again, this guy has no alpha hydrogens, right? And it will not undergo a self-Claisen condensation, so we should be able to do a crossed Claisen condensation reaction with this. So let's think about how to do this in the forward reaction, in the forward direction. So if we start with this guy, okay, we want to deprotonate the less substituted alpha carbon, okay, because we have two alpha carbons we can choose from. We've got this alpha carbon here and this alpha carbon here. This is less substituted. This is more substituted. So we need to think back and say, okay, how do we deprotonate something where we specifically want to go and make this guy here, so then we can react him with that ketone to give us, with an acid workup, this molecule, which is what they're asking. So how do we do this first step? So if you remember back, we can use lithium diisopropylamide, or LDA, in ether, and that deprotonates the less substituted carbon. Okay? So, if maybe it's been a minute since we've done that, I would suggest going back and reviewing that particular reaction. Now, the Claisen condensation, like the aldol reaction, has a potential for an intramolecular reaction, ultimately producing a ring. When it does this, it's called a Dieckmann reaction. It's named after the German chemist Walter Dieckmann, who worked on this particular reaction. And so an example of this is one that involves a diester. So there are two ester molecules here. And what we find is that there's a deprotonation of an alpha carbon, right? And so then a nucleophilic attack by the enolate anion forms the ring here. As with everything, right? This reaction works most readily if we can get to a 5 or 6 membered ring, because that reduces the ring strain. So if we look at the Dieckmann condensation example here, okay, right, then what we see is that ketones are more acidic than esters, right? And so when we look at this cyclizes when the reaction is treated with sodium amide, and that gives us a 5-membered ring product here. And so what happens when we look at this is that there are alpha hydrogens here, and since they're more acidic, that's more likely to be removed to form the anion here that can then come over and attack that carbon, forming the ring. So deprotonation almost exclusively takes place here because ketones and aldehydes are so much more acidic than esters, and the more acidic alpha hydrogen is the one that's most likely to get deprotonated.